Hello everyone, on behalf of QuTEM, I'd like to wish you all a very warm welcome to today's webinar, and we really appreciate that you can join us. My name is Cara Poon and I'm a senior scientist at QuTEM, and I'll be your host today. Today's webinar will involve a presentation followed by a short Q&A session. And if you have any questions during the presentation, please feel free to write them in the chat box to the right. Your questions will be private, so please don't hesitate to send in your questions, as only our admins will be able to read them. We'll also try our best to answer all of your questions today, but if we do run out of time, we'll get in touch with you afterwards by email to answer them. Finally, after the webinar, we'll share a recording to the webinar as well, so please don't feel any pressure to take notes. And now it's my pleasure to introduce our presenter for today, Mathieu Coulomb-de Zoek, a senior scientist at QuTEM. Mathieu will be speaking about TEM analysis of lentiviral vectors for quality control. So with that, I'd like to invite Mathieu to take over the screen.
Yes, thank you, Cara, for the kind introduction. So today I will give you a glimpse of the analysis that we are performing at QuTEM using electron microscopy, and the focus of today will be the characterization of lentiviruses. So in this presentation, I will first introduce a bit the company QuTEM, after which I will show you some insights onto electron microscopy, so the method preparations that we have internally. And then we will dive into more aspects of the quality control that we have for lentiviruses. And after that, we will have room for questions. So first of all, a few words about our company, QuTEM. So we are located in Stockholm, in Sweden. We are a company focusing on electron microscopy services in our validated facilities. So we have a GMP certification. And for our analysis, we are using our proprietary software, GridC, which is used for data collection, but also for image analysis and for the generation of report. The team is composed of scientists, so experts from broad fields in life sciences and material sciences. But not only scientists, of course, we also have software developers, which have helped implementing all our image analysis methods. And of course, the quality assurance department is an important aspect of our company. So if you look at our customers, we have customers all over the globe, mainly the Northern Americas and Europe regions. And our clients are mainly working in the life science and pharmaceutical areas, working with drug and gene delivery as well as vaccines. And the good thing about electron microscopy is that it can provide support through the whole development and production phase of drugs, so all the way from research and development to the batch release. And we typically like to try to accompany our clients all the way. So the type of particles that we are working with, as I just mentioned, are mainly drugs. So you can see here, you can have a glimpse of the different type of particles that we are typically working with. So you can see it's mainly viral vectors and other type of drug delivery vectors. And also on the right, you can see the type of analysis that we are typically performing. So of course, depending on your particle type, we will have different types of analysis that will be performed. The focus of today will be lentiviral vectors. And maybe one slide about lentiviral vectors. Nowadays, one of the main used for lentiviruses is for CAR T-cell therapy. So as most of you are already more familiar than me with this type of therapies, but in brief, the idea is to take some T-cells from a patient or from a donor and then transduct into them some gene that is then fed back into the patient. And to do so, of course, you need to deliver the gene, which is done via a vector, typically a virus. And that's why you have the whole viral vector bioprocessing first phase, where you will produce your virus with the gene of interest that will be later on transducted. So the market of the T-cell therapy, it's a very growing market. It's projected that in the next 10 years, the market should keep growing. And the technology was introduced in the 90s with the first approved product in 2017. And nowadays, the market have 6 approved drugs and a lot of ongoing trials, clinical trials. When it comes to the vector that is used for T cell therapy, there are a lot of different possibilities, but of course, lentiviral is actually one of the most, or it is the most, or the predominant vector which is used for the delivery and transduction of the gene. And that's the focus of today. And when it comes to what TEM can do, or the phase in which during the whole process where TEM can be useful, is typically during the viral vector bioprocessing. So from the production of viruses and encapsulation all the way to the purification of the virus prior to the transduction. So the focus of all the images that we will see today are typically done in this phase during the bioprocessing. Now, a few words about the method that we are using here at QuTEM, transmission electron microscopy. So in this one slide, I tried to summarize all the aspects of transmission electron microscopy. So that's a fairly dense slide, but I hope after that you will have more insights on how TEM is working and how what are the methods that we are working with. So first off, how an electron microscope looks like. Typically, it's very analog or very similar to a light microscope. So you have, instead of a source of light, you have a source of electron that you see here on the top. And then you have to imagine that instead of optical lenses, you have magnetic lenses that will create a magnetic field with which you will condense or spread your beam of electrons. And of course, you put your specimen in between those lenses, and then the beam of electron will go through it, and you will end up having a magnified image that you can see on your detector. The interest or the reason why we are using electrons instead of light, of course, it's because electrons can have way shorter wavelengths than that of light, so you can see subvisible particles, basically. So that's the whole idea of electron microscopy. So when working with electron microscopy, of course, we need to place our specimen onto a support. Typically, those are grids, so copper grids, which can have all sorts of mesh size and shapes. But the most common ones that we will be using here at QuTEM, but also in general in the world of electron microscopy, are copper grids, 400 mesh covered with a thin film of amorphous carbon. And then you will deposit your specimen onto that film, basically. As you can imagine, I just mentioned we are using amorphous carbon. Carbon is very hydrophobic. And most of the specimens that we are working with, especially in the life science, they are on aqueous media. So prior to depositing your specimen, you need to have a step called hydrophilization of the grid. Because you can imagine that, would it be that I take my lentivirus specimen and I place it directly onto my grid? It will not spread properly. So I will have a droplet, and then, of course, that's not what I want. I want to have a good spreading. So what we do is we place the grids prior to sample deposition. We place them into a small chamber in which we have 2 electrodes, and then we apply a current under low pressure condition, so that the gas which is present in the chamber will glow and will be ionized. And then charges will deposit all over the chamber, and amongst others, they will deposit onto the grid as well. So the carbon after that will be charged. So will it be that I take again my grid after this hydrophilization step and I place my specimen, then I will have a proper spreading, and therefore a more homogeneous spreading of the specimen. So that's it for the very basics of sample preparation. At QuTEM, we are using mainly 2 methods, namely negative stain preparation and cryo-TEM. So I will give you a few insights on these 2 preparations. The first one, negative stain. So we take an hydrophilized grid, and everything is done in negative stain at room temperature and directly on the bench or under a fume hood. So we apply the specimen, we let it adsorb for a while on the grid. We blot away the excess, and then we typically add a washing step. So the washing step will help to remove all particles or impurities that were not properly stuck on the grid. And after that, we are adding a staining agent, so typically uranyl acetate, so some salts of heavy metal that will have the role of embedding the specimen to protect it from the vacuum, from the column, because something I didn't mention is that in electron microscopy, your specimen is placed in a column with a very strong vacuum. So the staining will help embedding the specimen and preserving it from the vacuum, but also it will play the role of contrasting agent. And that's the reason why we are using heavy metals that are very dense electronically, and that will help to enhance the contrast of the particles. But as I mentioned, all of this is done at room temperature, and it's a very straightforward method with its own advantages and drawbacks. I will come back to that later on. The other method that we are doing, it's a method that was developed in the 1980s. It's called cryo-TEM. So in cryo-TEM, it's a similar kind of preparation. So we use the exact same grids as the one that we will use for negative stain. We first hydrophilize them, then we place the specimen onto it. We blot away the excess after a short adsorption time. And then what we do is we plunge freeze the specimen into some cryogenic liquid that will make it go directly from room temperature to cryogenic temperatures. And the idea here is to form ice, but amorphous ice, so ice in a way that it doesn't have any crystals in it, so that will not diffract the electrons. So from the time the grid has been plunge frozen, then we keep it in a cryogenic temperature, so in liquid nitrogen, all the way to the imaging. So this is a very brief overview of the whole methodology that we are using. But now, in the next 2 slides, I will talk a bit more about the differences between NSTEM and cryo-TEM. But before that, I would like to show you a bit how cryo-TEM is done, because, just to give you more insight. So that's the machine that we are using for cryo-TEM preparation. So you can see here that you have a specimen chamber, which is under controlled humidity, in which we apply the specimen, after which it goes. It's blotted away using these blotting tabs. And then we have a guillotine system that will directly plunge freeze the specimen into this small cuvette in the center. Typically, we are using liquid ethane. So you might know that liquid nitrogen is really available a lot in laboratories. So we could use liquid nitrogen, but the reason why we use ethane is that the heat transfer of ethane is actually much stronger than that of liquid nitrogen, meaning that if you will put your finger into a liquid ethane, you will burn yourself more quickly than in nitrogen. And here, what we want to do is to freeze the specimen as quick as possible so that we don't have any crystalline ice formation. And that's the reason why we use ethane. But from the point the grid has been frozen, then we can transfer it into liquid nitrogen and keep it into nitrogen for the rest of the process. So some key differences and key similarities between the two methodologies. The first one is about the scale of specimen that we can work with. Typically in electron microscopy, you work with specimen that go from the nanometer range up to the micrometer. So in terms of nanometer range, it can be down if you are doing structural biology, which is something we don't really perform here. But if you do structural biology using cryo-TEM, you can go below the nanometer resolution. But here we work mainly with direct observation of particles, so we can see objects down to, I would say, down to the antibody size, down to big protein sizes, basically. And up to a certain limit, of course, because you can imagine that the bigger your object will be, the less easy it will be for the electrons to penetrate it. And therefore, when we start to reach a micrometer range, then the particles start to get darker and darker. And would it be that we want to see them, we need to increase the electron dose, and then we start having damaging the sample, typically. So that's why the particles we're working with are typically in the range of a few tenths of nanometers up to a bit less than a micrometer. So for that, viruses is a perfect match, actually. When it comes to the embedding of the two methods, so as I mentioned earlier, in negative stain, we use a heavy metal stain, while in cryogenic TEM, we just use water, so vitreous ice or amorphous ice. And when it comes to the main highlights of the two methods, so the strength of negative stain is that you will have a stronger contrast or even a high contrast on your images, and therefore you will be able to spot more easily the small structures. while the drawback is that since you add some stain, you cannot really see the internal features of the particles, which is something that can be done with QuTEM since there is no other agent. So you really directly look at your particle and you can see through it. So to assess the particle packaging, QuTEM is a very good method, for example. And also an advantage of QuTEM over negative stain is that you preserve your specimen into it's close to its native state, so it remains hydrated through the whole imaging process. While in negative stain, as I mentioned, we are working in the open air, and we are blotting the specimen, meaning that you might dehydrate or you might alter the particle morphology just by the very preparation. Also, adding some salts can add some stress to the specimen in terms of pH, also in terms of when you are blotting, you can have draining effects that apply some physical stress to the specimen. So more things can go when you are doing negative stain preparation. So it's more straightforward and it's useful to assess small structures, but when it comes to looking at the internal structures or looking at the overall integrity, QuTEM can be a good method. Then when it comes to the analysis type, so we will dive more into that in the next slides, but when it comes to the applications, typically negative stain can be used to assess the aggregation state, also looking at small impurities, and of course looking if some particles are broken or not. While in QuTEM, you can do some of these things as well, but also you can more easily look at the particle size and as well as the vector content, as I just mentioned. So just one slide to show you a direct confrontation or direct differences between QuTEM and negative stain. So here you can see a cross-section on how particles will look like. So you can see that you have the carbon film, then you have your particles which are deposited onto it, and then you have the stain that embeds the specimen. And the reason why it's called negative stain, I didn't mention it yet, but it's of course because we are using heavy metal with a high electron density, so that will appear dark on the images, while your particle itself will appear more bright. And that's a bit what you see here. You can see the edges are darker because the stain thickness there is a bit higher. So here you see some interesting examples of lentiviruses in negative stain. And next to it, you have a similar sample with a QuTEM in which the specimen was embedded into vitreous ice. And directly here from the two right images of each method, you can really see that in the case of QuTEM, you can already see that there is something inside the particles, so you can really look at the internal features of the particles. So in the next couple of slides, I would like to show you some more examples of what we can typically analyze at QuTEM when it comes to lentiviruses. So maybe one of the aspects that we can assess, at least qualitatively, is the aggregation. So of course, you might know that if your particles are aggregated in the case of T-cell therapy, the transduction will be greatly affected by it, and you will have a poor efficiency of the transduction. And typically, we observe that aggregation happens during the filtration processes or during the purification of the particles of the drug. So this is something that the customers like to ask us to assess the aggregation of the specimen. And that's something that we can do, as I mentioned, at least relatively by looking at two specimens or two samples, one before filtration and the other one after filtration, and then looking at how large the aggregates are and see if we see more aggregates in one than the other. So again, you see here two examples, one in negative stain and one in QuTEM. This type of analysis can be performed, of course, using both methods. So that's for one. Another key attribute that can be evaluated using TEM is the particle integrity. So of course, here during your processing, you might have steps that will affect the particle integrity, and you might end up with broken particles, which will, of course, result into less efficacy of the drug. This particle integrity can be performed directly or morphologically, so by directly looking at the morphology of the particles, so we can easily assess which particles appear intact on the images and which particles appear broken. And that's something that can be easily done. And yeah, in TEM, of course, it's a very good method in that you can directly see your particles, so you can directly not only identify, but also easily characterize and classify them. So that's one thing that can be performed. So here I show an image typically using negative stain. Of course, one could think of doing the same with the cryo-TEM as well. Another step, which on another quality attribute that can be evaluated is the purity. Also here, the purity can be assessed before the purification and after the purification, for example. So you see two examples here of a similar specimen during two different stages of the development. And also here, you don't need to be an expert to see that in one image you have less impurities than in the other. And of course, here the purity is a key element to be evaluated during the bioprocessing, as it can affect the transduction, of course, also here. In this case, I showed some cryo-TEM images, but also for this type of analysis, we could think of looking at the impurities using negative stain, especially if we want to characterize impurities. Maybe negative stain could be more appropriate in that you have a better insights onto small objects in negative stain due to the higher contrast. Another element, another attribute that can be assessed is the maturation, or in this case, the packaging. So within one sample, you can really see different types of particles, all of them being at different stages of the packaging. So you can see the fully mature particle that encapsulates the genome with its typical cone structure. But you can also see empty particles, and also you can see some of the some exosomes. I guess here we are seeing probably. So you can see a whole range of particle morphologies. And once again here, TEM is a very powerful tool in that you can really not only look at the data, but actually relate the data to the image and therefore to your particle. So packaging is something that is typically performed using cryo-TEM, since in negative stain it's very hard to see inside the particle. Yeah, last attribute I would like to talk about today is the size distribution of lentiviruses. So typically here you see an image that on which we can detect the particles. Having insights onto the size distribution can help onto different aspects. One of them is for the identification of impurities or at least of non-wanted products. Also here, TEM is quite powerful thanks to the direct visualization of your particles, in that if you would use other methods like DLS, for example, you would have several peaks, but then it will be hard to attribute peaks to actual populations or to actually characterize each peak. While here, again, you can directly relate the peak to the image. So if you see two peaks, you can see, oh, this is my individual particle, and this peak, which is a bit broader, maybe it's two particles which are next to each other, or maybe it's something completely different. Maybe it's an exosome, or if it's smaller, maybe it's some subunits which are not properly assembled. So in this case, yeah, TEM is a very strong tool in that it helps you to characterize the particles and the peaks. So yeah, that's it for a general overview of the different quality attributes that we can perform here at QuTEM for the lentivirus characterization. In the last slides, I would like to tell you a bit more about the workflow, so the typical workflow that we are having at QuTEM, to give you a better idea of what will happen. Would it be that you send us some samples? So the first steps, of course, are to agree on a project and a project description and a quotation. But once we have all the elements for the project, we receive the specimen in our BSL2 facility, in our lab here in Stockholm. So first, the samples are stored until they are prepared and imaged. When it comes to the sample prep, we move the specimen to the lab, where we are preparing them depending on the method, so negative stain or cryo-TEM, according to our protocols. And then, of course, everything is performed by qualified personnel. Once the sample has been prepared, we move to the interesting part, to the TEM imaging, where we start to actually see the particles and the images. So the imaging is done. We have 2 microscopes here that can perform equally well. And then we are acquiring a set of images. Typically, we acquire a broad data set that is representative of the whole specimen. Of course, we try to go at different areas on the grid to try to be as representative as possible. And from that point on, from the TEM imaging part, everything is fed into our software, GridC, in which we are doing the record keeping, not only for the images, but also for all the steps from the lab, since the software is qualified. And therefore, we are doing the image recording, but also the image analysis. So I can move on to the next slide. So here, you can see that we don't have lentiviruses, but here we can see some AAVs, for example. So would it be that you have something else than lentiviruses? Of course, we can talk about it and most probably analyze it. But the image analysis is done in our software, GridC. So we are trying, of course, to implement new detection methodologies, but also new classification methodologies, especially nowadays with the AI coming up. All of this, of course, under validated and under the supervision of the QA department. So once we are done with the image analysis and we have a whole representative set with strong enough data, then we start to write a report. And then this is what will be delivered to the customer. So here you can see, again, this is an example report of AAV particle, but would it be that you want to see how a report for lentiviruses looks like? You can go to the handouts section of this webinar, and then you will find an example report. But typically, we compile all the most important information in the report, so some representative images, and then some whichever data was asked or required by the customer during in the quotation. And once we are done with this report, then we have an independent review that will go through the whole project and make sure that everything is fine. And after that, we hand over the report to the customer together with a set of representative images. And of course, through the whole process, we are open to discuss with you, especially at the beginning and after we have delivered the report to help you interpret the data. So that's it for today's presentation. I hope I managed to give you some broad overview of how QuTEM can contribute to the characterization of lentiviruses. And also, I hope I gave you some insights or more insights into transmission electron microscopy. And right now, thank you for your time. And I'm open to any questions you might have. Feel free to ask them in the chat. Thank you.
Thank you, Mathieu, for your presentation on lentiviral vector analysis using TEM at QuTEM. So now we'll have just a short Q&A session. If you haven't sent in your questions yet, please feel free to do so. It's in the chat box to the right. So with that, I think we already have some questions, so we can just get started. The first question we have is, what's the turnaround time when sending samples in for lentiviral vector analysis?
So thank you for this question. So the typical turnaround time is 10 days. So from the time we receive the specimen or the samples, we store them, and then we agree on a starting date. And from the time we have been starting the project, it will take 10 days, including sample preparation, imaging, image analysis, reporting, and then sending away the report.
Okay, and then the next question we have is, what biosafety levels do we handle here in our lab?
Okay, thank you for this question. Our lab is a BSL-2 laboratory, so we are working with the maximum BSL-2. So typically, lentiviruses used for T-cell therapy, they are typically within that range of BSL-1 to BSL-2 samples. So the way it's done is prior to agreeing on the project, we ask for some information about the specimen so that we can run a risk assessment. And once the risk assessment has been run, then we can, of course, agree on the project itself and then receive the samples, so all the way from BSL-0 to BSL-2. Okay,
and I think we have time for one more question. So is the quantification of viral particles, for example, intact, broken, packaged, or empty particles, is it performed manually or is it done by our software?
Yeah, so that's a good question. So whether it's done manually or directly by the software depends a bit on the particles type. But typically the detection itself, so the part where we go from just the image to segmenting the particles, this is done using some algorithm and some fixed methods that we have in our protocols. So first we have automated detection. After that, we have a manual curation. So a qualified analyst will go through the images and make sure to uncheck all the particles that were wrongly detected and add the particles that were not detected. So the performance of this detection varies a lot on the particles type and on the purity or say or the background, of course, of the images, as you might imagine. So for example, with AAVs, we have very strong and robust methods where I would say 99% of the particles are properly detected to start with. While with the lentiviruses, as you can see from the images we have here, there are always a lot of background debris. So the efficacy of the method is not as good as for AAVs, but still it helps a lot and helps us to gain a lot of time. And we always have, anyway, no matter automated or not, we always have a visual check by a qualified analyst. So that's for the detection part. When it comes to the classification, once we have detected our images, we need to classify them. Also here, it depends a lot on the particle type. So also for AAVs, we have very robust method that help to not only discriminate between full and empty, but also look at the internal density to evaluate the genome length, for example, or intermediately packed particles. So that's for AAVs. When it comes to lentiviruses, I would say that most of the classification part is done manually nowadays. So we typically look at the particles and then classify them manually. We have some tools that help with the classification, but yeah, it still is a lot of manual work. And we are implementing also nowadays some other AI tools, such as support vector machine, SVM, for example, for the classification of other particle types like VSV, if you are familiar with it, for example. So yeah, so I would say in brief that we always try to have as much support as we can from our software, but no matter the data, it's always verified by a trained and qualified analysts. Yeah.
Great. So I think that's about all time we have for today. Before we go, I'd like to remind you that we've also shared the example report for lentiviral vector analysis for information. You can find that in the handout section of this webinar. We'll also keep this webinar session open for a couple more minutes afterwards so that you have time to download it. We'll also send you a link by email to access a recording of today's webinar. So if you have also any further questions, please don't hesitate to get in touch with us at info@QuTEM.com. And finally, on behalf of QuTEM, I'd like to say a very big thank you for joining us online today. It's been a pleasure to present our analysis to you and also for all your questions. We look forward to also getting in touch with you in the future. Have a great day and thank you.
Bye-bye.
Bye.